got him in between. Actually, he remembered the call, he remembered who was there.
Oh, anyway, you are.
It's also not very convenient. Clock is slow, it's already 5:40.
We are running 20 minutes late.
I just came to say hello and.
We've been watching this on YouTube.
Oh, you can watch it.
Most comfortable. No, I understand.
Hello. I hope you're on your seats with your minds alert. So we're going to get a speaker for you that I don't have to introduce because I notice that there are many students here and most of you might have already known him on the Great Net. Anyway, he's been teaching physics in Chennai for nearly half a century. I think it might be a record. And he'll be talking to you today about the topic which is on the screen. And whether you're allowed to ask questions or not, I think the speaker will address that issue. He didn't tell me whether can they ask questions?
Of course.
Oh, so you're welcome to ask questions and enjoy the talk.
How do I move backward and forward?
Forward?
The backward, huh?
Yes, sir.
Okay.
Do you need a chair?
No, I stand, prefer to stand. Thank you. Shall I start? Thank you very much, Ramesh. And let me start by thanking Professor Ghosh and Professor Bhaskaran and the other organizing committee members for inviting me to give this talk at this meeting. I've written my talk out, so I'll be essentially reading it out because I no longer have the confidence that I can do this extempore. So I hope you'll forgive me for that. The talk is somewhat technical, I should apologize for that also. I realized, I first thought, if it's an evening lecture, I should make it a general kind of talk. And the only general topic that I could think of which would be appropriate was something about the history of quantum mechanics. And then when I looked at it a little more deeply, I realized that I didn't know enough about the history of quantum mechanics to venture such a talk. So I thought, let me talk about an elementary aspect of quantum mechanics, partly, of probability theory really, and relate it to some quantum problems which are done in textbooks and courses and so on. So that's what I'm going to do. This talk is, much of this talk is based on this article that we wrote. It's going to be published, or I don't know if the hard copies are already available, but the online publication is over. And it's in the Journal of the Indian Institute of Science, a special issue to commemorate the 100th year of quantum mechanics. So those who are interested, the TOI is there. So probability and statistics pervade all of science, much more so in modern physics. Quantum mechanics in particular is inherently statistical in nature, as we know. In general, how do you describe the state of a quantum mechanical system? You use a density matrix rho, or also called the statistical matrix in the old days, and applies both to pure states and mixed states, to isolated systems as well as closed systems, as well as open systems. Here. Using this density operator, one can compute in principle the expectation values, all the higher moments and so on, and all the correlations of all the observables involved in the system. In particular, we can deduce the probability distributions of the individual observables. This is in principle. In practice, it's a very different matter altogether. So the natural question that arises is, how do you tell the difference between two probability distributions of a given random variable or given observable, corresponding respectively to two different states of the system? How do you do this quantitatively? And that's what we are going to address today. This is not only a basic question in probability theory, but also one that has numerous important practical applications, not necessarily restricted to quantum mechanics itself. It's a very general problem in probability and statistics here. Such as, for instance, to talk about some problems of today, pattern recognition, image reconstruction, tomogram interpretation, and all such information theoretic tasks, they require the quantitative estimation of how close or how far apart two probability distributions of a given variable are. So that's a basic problem in probability theory for which a lot of literature exists. Okay. There are many quantifiers of the way in which two probability distributions diverge from each other, or a pair of probability distributions diverge from each other, or the distance between these two in the space of probability distributions here. Our interest was spurred by the fact that we are interested in the problem of the possibility of using some of these quantifiers to distinguish between different states of light arising in quantum optics, especially coherent states, squeezed coherent states, displaced coherent states, and so on and so forth. Specifically, we will talk about three quantifiers, in fact just one, the Wasserstein distance, but we will start with three quantifiers, the Kullback-Leibler divergence dKl, the Bhattacharya distance dB, and the Wasserstein distance, the one Wasserstein distance technically, which I'll call W1. We'll begin with the definition of these quantifiers, followed by their application to some case studies in quantum mechanics to bring out the dependence on quantum numbers, and that's going to be our primary interest, one of our primary interests. This quantifier, how it depends on the quantum number of the state concerned and its associated probability distributions. And then we'll apply it to various states of light. So a little bit of definitions here. For definiteness, let's consider a random variable x running from -infinity to infinity, taking values in -infinity to infinity. The extension of what follows to the case of a semi-infinite or finite interval, as well as the case of discrete random variables like integer valued random variables, is very straightforward. So let small f and small g be two different normalized probability densities of PDFs of x with corresponding cumulative distribution functions given by capital F and capital G. Capital F is essentially the probability that the random variable has a value less than or equal to x, and similarly for the other one, for the second distribution. Now this cumulative distribution function is obviously a non-decreasing function of x, with f of -infinity equal to 0 and f of infinity equal to 1. So this function takes values between 0 and 1, and it's non-decreasing. The so-called Kullback-Leibler divergence, introduced long ago in the information theoretic context, between which PDFs f and g is given by this expression that I've given here. It's essentially the average value with respect to one of the distributions, f of x. I'll use the word distribution and density sort of interchangeably, although I've been careful in writing to distinguish between them properly. But speaking wise, we often say probability distribution when we mean a VDF and not a CDF. It's the average value with respect to f of x of the log of f of x over g of x here. This is a measure of how much the PDF g deviates or diverges from the reference PDF f. The Bhattacharya distance between f and g is a cheap version of the Kullback-Leibler divergence, and it's minus log the integral. Notice that the log appears inside the integral and the dKl, whereas it appears outside the integral in the Bhattacharya distance. Okay. So this is a very quick check of how much these two deviate from each other. DKL is also called the relative entropy or mutual information and quantum information science, but I'm not going to get into that. And DB are rooted in information theory. DB is symmetric under F and G interchange, but DKL is not. But neither DKL nor DB is a proper distance functional in the space of distributions, because the triangular inequality is not satisfied, for instance, and then one of them is not symmetric even. But they have their uses. A very different kind of measure is the so-called Wasserstein distance or earth movers distance, which is familiar to computer scientists. They call it earth movers distance, stemming from optimal transport theory. The so-called P Wasserstein distance, WP of F, G, is defined in terms of the inverse CDFs or quantile functions of the probability distributions as an integral from 0 to 1 dq, F inverse Q minus G inverse Q, modulus to the power P, the whole raised after the integral to 1 over P. It's obvious that this is a symmetric measure under the two and interchange of the two distributions concerned. It is a genuine distance measure in the space of probability distributions for CDFs F and G. For three CDFs F, G and H, we have the triangle inequality satisfied, so it's really a proper distance measure in the space of distributions. It has its limitations, but we'll see what they are as we go along. In the P equal to 1 single random variable case, which is all we are going to consider here, a change of variable of integration leads to a formula which is very interesting. It's W1 of F, G is an integral from n over the range of x, minus infinity to infinity in general, mod f of x minus g of x. The modulus is crucial so that the whole distance remains positive. It also means that you can't do this integral so trivially. You have to be a little careful, because neither integral dx f of x nor integral dx g of x converges, because both f and g go to unity as x goes to infinity. And we'll see how to fix that. Another important observation is that while DKL and DB are dimensionless, W1, the Wasserstein distance, has the physical dimensions of the random variable concerned. Further, since f and g are inside the unit interval for all x, it's obvious that W1 is bounded by the length of the interval, which could be infinite, on which x takes values. So here's a pictorial way of understanding this. You have a probability density f of x, and you have another one g of x, and you want to shift this f of x and reconfigure it, shift it and reshape it so that it becomes g of x. Or you can dig a well in the shape or a pit in the shape of g of x minus g of x, and you ask what's the cost of moving the earth from the pile f of x into to fill the pit minus g of x exactly. So each of these, the pile and the pit are completely filled and flat. So the cost here is the amount of mass of earth that you move from one place to another multiplied by the distance that you move it by. And you want the optimal value of the optimal way of doing this. This problem was actually posed first by Gaspard Monge in the 17th century, 18th century, and the problem is still unsolved in its complete generality with multivariate case. It's not exactly solved as yet. It's one of those very tough problems. I've already said that you need care in exercise care in doing this integral, because of the integrals could diverge. But it's easily fixed. Instead of the CDFs f and g, let's use the survivor functions sg and sf, where sf plus f is equal to 1. And similarly for g. So it's the residual function or the survivor function for the distribution concerned. It's the probability that the variable has a value greater than or equal to x. Then this W1, it simplifies to the integral of the modulus of the difference between the two survivor functions here. And let's see how that helps us. For example, consider two exponential distributions with PDFs, exponential functions running from 0 to infinity, with distribution functions that are two exponentials, ae to the minus ax and be to the minus bx. Then it's easy to calculate that integral that I wrote down, the residual functions difference, and the answer turns out to be mod 1 over a minus 1 over b, which you could have predicted beforehand, because after all the only scale in the problem is a and b in the two distributions. Similarly, it takes a little longer, but a short calculation shows that the WD between two normalized Gaussians centered about the same point, it doesn't matter which point, but with different variances sigma 1 and sigma 2 is given by square root of 2 over pi mod sigma 1 minus sigma 2. So it's a sort of physical picture that you have a sharply peaked Gaussian and you have a flat Gaussian, different variances, and the modulus of the difference of the standard deviations is in fact your Wasserstein distance, apart from this constant √2/pi. So I should at this stage make a disclaimer. In recent years, a huge amount of work has been done on a mathematically rigorous formalism, extending the notion of the Wasserstein distance WP to define quantum analogues of WD for cases of general multipartite quantum mechanical systems, the states themselves. So they don't talk any longer about the probability densities or functions, cumulative densities, etc. of various random variables, but they talk about the states themselves directly, asking like, you have a chain, spin chain for instance, with different states up and down, etc. in all permutations, and you could ask what's the different distance between these two in the sense of Wasserstein. It's not quite the same thing as asking what the Hamming distance is, for instance, but I'm not going to get into this because it's a subject by itself. Okay. My purpose here is to actually use very simple quantum mechanical examples to show what the Wasserstein distance can do and can't do. So let me go on. And we'll start with the most basic quantum mechanics, some simple examples. So if psi is a normalized pure state of a particle moving on the x-axis, then the density matrix is just the projector psi, and the PDF of the position of the particle is given by mod x psi inner product mod squared, which is what we call the modulus squared of the wave function psi of x. Similarly for another wave function phi of x here. More specifically, we are interested in looking at families of such functions for a system, like for instance the eigenstates of the eigenvalues or eigenstates of a potential of a particle in a potential, for instance. So let mod phi n x squared n running over 1, 2, 3, etc. be the orthonormalized positional PDFs of the energy eigenstates of the particle labeled by the quantum number n. As physicists, our immediate interest is to ask what's the asymptotic behavior. It's of interest to analyze the n-dependence of the distance between these distributions in the ground and excited states, particularly its asymptotic behavior as n tends to infinity. It's a very reasonable question to ask. We're all taught in elementary quantum mechanics about eigenfunctions and eigenvalues of the energy operator in Hamiltonian and one-dimensional problems, but we hardly ever, in fact I haven't seen any textbook that asks this question and says what's the difference between the probability density functions itself. It has some surprises, as we'll see. So let's look at our canonical simplest quantum mechanics 1 example, particle in a box between 0 and 1. It's very often said free particle in a box, but the particle is not free, it's inside a potential. So the potential is infinite outside the box and 0 inside the box. So then in that sense it's free inside the box, but of course its momentum is not constant and its eigenstates, eigenfunctions of the Hamiltonian. The Hamiltonian doesn't commute with the position or momentum operator in this case. One has to be careful here. So the energy eigenvalues are proportional to n squared, where n runs from 1 to infinity over the integers. The PDF itself is just 2 sine squared n pi x. I've set the length of the box to 1. The classical PDF is 1 on the other hand. The cumulative function is x minus sine 2 pi n x or whatever it is. So if you compare it with the classical distribution of this particle, whose probability density is just uniform over the unit interval, then you can find out what the Bhattacharya distance is, and it turns out to be this number log pi over square root of 8. Similarly, the Kullback-Leibler divergence turns out to be log 2, and in the other reverse order it turns out to be 1 minus log 2. There is no n dependence at all of these measures on the quantum number. And the reason is, of course, that the classical limit is n equal to infinity, and for when you're looking at it from n equal to infinity as a reference point, n equal to 2 or 3 or 4 doesn't matter at all. So therefore it's expected that there is no time n dependence on these measures here. You can now ask what does the Wasserstein distance do, and then this is a very different thing altogether. You get this integral of the modulus of a sine function and it becomes 1 over n pi squared, which decreases monotonically from 1 over pi squared to 0 as n increases from 1 to infinity, as shown in this plot here. So there is strong n dependence here. It's interesting that this PDF Gn 2 sine squared n pi x has finer and finer comb-like forms, and the picture shows n equal to 1 and n equal to 5. But when n tends to infinity, it's a rapidly oscillating comb up and down, but the maximum of the comb is always at 2, and the minimum is always at 0. And this becomes a finer and finer thing. So the Wasserstein distance between the classical and the Gn, the nth state, goes to 0 as n tends to infinity, as you would expect, although the probability densities are not the same. So it's as if you have got a flat line for the classical state and for the classical distribution, and then you have this fine Dirac comb-like structure, except that the comb teeth are closer and closer to each other and getting thinner and thinner, and then the Wasserstein distance between the two tends to 0, even though the distributions are different, because all it takes is just a puff of air in order to blow this house of cards down and make it flat completely. So it's an interesting case where the Wasserstein distance can tend to 0, but the distributions don't go to each other. This distribution has no limit, it just, the oscillating distribution keeps going up and down forever. So already there are interesting features. So here this shows n equal to n and n equal to 5 in the language of the cumulative distribution function. This is what it looks like. And the Wasserstein distance between G1 and G5 is just the sum of the areas between the two lobes, or of the two lobes concerned. You can see that they change sign in between. Next, let's consider the Wasserstein distance between the ground state G1 of x, which is after all the normal state of the system, and Gn where n greater than 1. Interestingly, there is a very strong dependence of this W Wasserstein distance on the parity of the states concerned. For n equal to 2, 4, etc., the odd parity states, the W remains at or close to the constant value 1 over pi squared for every n value. But when you have an odd parity state, even parity states, Wg1, Gn increases from 0 and approaches the limiting value of 1 over pi squared from below as n increases. This is what it looks like. So the black dots show you how the same parity states go up and saturate, and the other one shows how right from the beginning the opposite parity states compared to the ground state already are at the saturation value of the Wasserstein distance here. Heuristically, this difference arises because of the parity of the PDFs concerned. They have the ones that are even ones, that's G n equal to 1, 3, etc., even in this notation since the ground state is n equal to 1. They have a prominent central peak at half, while the odd parity PDFs G2, G4 have a central minimum. This implies this dominant contribution to the WD between G1 and G2n. Other intricate features occur in W1, Gm, Gn for general m. As n tends to infinity, W1 of Gn, Gm tends to 1 over m pi squared. Instead of 1 over pi squared for m equal to 1, it's generally 1 over m pi squared. So you can see there's a lot of structure buried in these things. Before I go to orbital angular momentum, I should also give a homework problem. One can ask what happens if you have power law distributions instead of nice functions like this. You have infinite range and a power law distribution. So I urge students to work out what happens to the Wasserstein distance for momentum space probability density functions. So take the Fourier transform of the position space density function and take the mod squared of it. That gives you the momentum distribution, which for a particle in a box in any energy eigenstate is an extended distribution running from minus infinity to infinity. The ground state goes like some cosine function over p to the 4, to the 4th power. Work out the difference for the Wasserstein distances in this particular power law case. It's an interesting exercise. By the way, I can't resist saying that this incredible set of books called the Landau-Lifshitz series actually has the momentum space wave function worked out for the ground state of the particle in a box. The only place I've seen it there, I've seen this particular thing considered specifically, but it works out only the ground state. And it's 1 over p to the 4, which shouldn't surprise you because it's a power law, because you've localized the particle within the box, and therefore the Fourier transform by the Paley-Wiener theorem has to be very extended, goes all the way to infinity. It's a power law. It cannot go like it must be even in p, so it must be start with 1 over p squared, but that would make the expectation value of p squared infinite, which it is not because it's a finite, the energy value apart from the mass factor. Therefore, the only thing it can do is to start from 1 over p to the 4. Okay. Having done the one-dimensional problem, let's look at having done something which is the canonical standard problem in quantum mechanics, physics, quantum mechanics 1. Let's ask what happens to angular momentum eigenfunctions, or a set of probability density functions generated by the Legendre functions here. we should really use spherical harmonics, but let's use the case m equal to 0, and then we have the Legendre functions, and m equal to 0. The spherical harmonic reduces to the Legendre polynomial, taking values from -1 to 1. From the orthonormality relation, it follows that you can find a normalized PDF, fn of x, which is essentially the square of the Legendre function, Legendre polynomial, apart from that normalization factor n plus half. And if you plot it, it looks like this. I must confess, after so many years of familiarity with Legendre polynomials and so on, related spherical harmonics, it came as a surprise to me to see this graph. I was very surprised. If you take mod Pn of x whole squared and plot it as a function of x against for various values of n, and what's been plotted is just for 3 sets of values here, most of the time the graph is 0. It's very close to each other, but you can see the wiggles are very close to 0 on the vertical axis, and they're not very distinguishable from each other except for the spikes at the end here. So what this tells us is that you shouldn't be surprised if the Wasserstein distance for different values of n is essentially the same thing when you compare it to the ground state. The ground state has a different distribution altogether. That's a constant altogether. It's a very different shape. But then it doesn't matter what n is. You compare with the ground state, which is p equal to 0, n equal to 0, then you get exactly the same answer. That's what we should expect. And let's see what happens if we plot it. You see how flat it is, this graph is. Apart from a little fluctuation for small values of n, the comparison with f naught fn remains essentially the same for all n. So the asymptotic behavior is already there once you reach n equal to 3, 4, etc. How about going a little further and doing the S-wave states of the hydrogen atom? Because that's over the Laguerre polynomials. So let's see. Setting the orbital angular momentum quantum numbers L and M equal to 0, the radial PDF is given by this function here. It's 1 over n to the power 5 e to the minus 2r over n, and then Ln minus 1, the associated Laguerre polynomial of 2r over n, the whole squared, in units of the Bohr radius. Principal quantum number is n, it runs from 1, 2, 3, etc. The normalization of this function is equal to unity from 0 to infinity over r. This is what the function actually looks like for the first 9 values of n, 1 to n. The ground state, there's the ground state of the hydrogen atom in the Bohr model, for instance. It starts at 0, of course, as it should, because of the phase space factor, and then it goes up and peaks at the Bohr radius and comes down, a single peak. And then when you do n equal to 2, 3, 4, etc., you have subsidiary peaks. You should note that the n equal to 1, 2, 3 has been plotted. Vertical axis scale is different from that of the remaining figures, so it's not to scale actually. What happens is as n increases, as we all know, the peak, the most prominent peak moves further and further to the right, which is what you expect. That's going to have consequences. If you plot the Wasserstein distance between the ground state and the end state for the S-wave states of the hydrogen atom, you get a nice parabolic shape like this. So it looks like it's fitting n squared. And the variation actually fits well with a quadratic function of n. The asymptotic n squared behavior has to be explained. As physicists, that's the first thing we have to do. Why is it n squared? On physical grounds, we can do this. The position of the dominant peak in Fn of r increases with n like n squared, because that's how the classical turning point behaves. Let me write it here. You write the energy balance equation, then the radial momentum squared over 2n plus L into L plus 1 divided by r squared minus the potential 1 over r must be the total energy, which goes, as we know, like minus 1 over n squared. Now, for the case of for the turning points, at the turning points the radial momentum vanishes, 0. At L equal to 0, the second term vanishes, so you end up with r proportional to n squared. So that explains why you have a quadratic dependence there physically. And now the lesson of the story of this example is that the Wasserstein distance is dominated by the distance between the two peaks of the two distributions concerned, because that's where the maximum Earth has to be moved from one to the other, the asymptotic case. How about generalizing this problem a little bit in one dimension? Let's do that by taking, yeah.
Here, we have a result which looks like n squared. That's the separation between the peaks, right?
Mm-hmm.
But initially, when you had the two Gaussians which had the same mean but different widths.
Sorry.
when you had the same mean and different widths, then
Right.
it depended on actually sigma 1 minus sigma 2.
Right.
So here the widths of the peaks don't seem to enter this expression at all, right? It's only the distance between the peaks.
Where? Which?
In your, this example of 1 versus n of your hydrogen atom, you get a behavior as n squared, right?
Well, finally, for large enough n, there are just two dominant peaks, and you have to move this pile of earth to that pile. That's
Yeah.
it.
No, but there is no dependence on the width or
Or the finer details,
Yeah,
they're
yeah,
subasymptotic. They're subasymptotic.
Oh, okay, I see.
If you do that on a magnified scale properly, you'll see slight fluctuations to the n
Oh,
squared
right, I see.
being. So it's not pure n squared. Asymptotically, the leading behavior is n squared.
I see.
I might mention that if you took two Gaussians which are not centered at the same point and don't have the same variance, then there is a contribution to the Wasserstein distance from the difference between the mean values, and then there is a contribution from the variances also. So the case I wrote down was when they're centered at the same point. So, yeah.
Suppose you put Rydberg scale, very high,
Pardon me?
Rydberg scales,
very high angular momentum, very high radial L value, n value, large n value,
Okay.
then compare the distance between two neighboring states. Is there any asymptotic behavior of that? Now you are comparing,
You're considering angular momentum states also?
I'm taking zero angular momentum,
Zero angular
but
momentum.
large n.
Yeah.
So then I'm comparing two such Rydberg states which are very large, n and n plus
yeah,
1.
Yeah.
So is there any systematic as a function of n?
Yeah, there is a system. I don't have that graph here.
Okay.
But it will essentially go to 0 as n tends to m.
I
That's
see.
obvious, it's going to do that. But it's, how it exactly it vanishes,
Because it may be important in the context of Rydberg atoms, highly excited states and so on.
I don't remember that result now, but it vanishes at n equal to m. And I suspect there's a term which is mod n minus m sitting there, the leading term. And we are more interested in finding out what the asymptotic behavior compared to the ground state is, which is what this thing is. Okay. So consider this Hamiltonian p squared plus mod x to the power 2 lambda. You put lambda equal to 1, you end up with a harmonic oscillator, and where lambda is a positive constant. Classically, the motion is periodic for every initial condition. The phase trajectories are just simple closed curves or ovals in the px plane. Quantum mechanically, the spectrum is completely discrete. The oscillator has a discrete infinity of infinite spectrum E0, E1, etc., with the ground state separated from 0. Although En and the corresponding eigenfunction cannot be expressed in closed form for general lambda, the leading large n behavior of this is easily deduced semi-classically. What would we do? If you do semi-classical quantization of find the area of this oval phase trajectory, the amplitude along the energy momentum axis is e to the power half, because square root of 2m is the maximum that you can have, and it's e to the 1 over 2 lambda in the x-axis on the position axis. So the area is proportional to the product of the two, which tells you En is proportional to 2 lambda over lambda plus 1. The level spacing, of course, is the derivative of this En with respect to n. Spacing decreases with increasing n for lambda less than 1 and increases for lambda greater than 1, and is the harmonic oscillator or equispaced for n equal to 1. On the other hand, if you ask what the classical turning points are, they are at x equal to plus or minus the amplitude on either side, and that's given by an squared. An to the 2 lambda is proportional to the energy. The energy is dependence on lambda n, we already know. So if you put both these together, it follows very easily. That the Wasserstein distance is proportional to n to the power 1 over lambda plus 1. So that's the closed result that you get for the asymptotic behavior for the generalized oscillator here. If you put lambda equal to half, then W1 goes like n to the 2/3. For lambda equal to 1, which is the harmonic oscillator, it goes like square root of n. So this is a special case of the generalized oscillator case, and tells you what it does. As lambda tends to infinity, the potential becomes steeper and steeper, and it's 0 within the unit interval, and or minus 1 to 1 or whatever, and infinite outside, and it goes like the Wasserstein distance goes like dot for a particle in a box. And if you put lambda equal to infinity here, you can see that the W1 goes to a constant. And remember, long ago when we did a particle in the box, we found the thing tended to a constant, and that's a special case of this exponent here. In all these cases that we looked at earlier, the PDFs were of the form mod phi n of x squared, where phi n of x is an orthonormal set of wave functions here. In the comparison between Fn and Fm, the most obvious and easily computed quantity would be the overlap or fidelity. So why you can ask, why am I bothered about this? Why don't I just look at the fidelity of these two states from which you want to compute the probability densities? Well, the point is that we are looking at orthonormal sets of functions, and therefore the fidelity vanishes identically for n not equal to m. So it's useless as a measure here. It just doesn't give information at all. But the Wasserstein distance, on the other hand, provides a clear distinction between the two distributions in this case. So it's not enough to look at the fidelity. Now let's look at the Wasserstein distance between number distributions. The quantifiers can be extended to discrete probability distributions. Let P and Q be two such distributions, and then we ask what happens. The density matrix of the radiation field, if you have a radiation field for instance, is P summation over n Pn, projection over the Fock states n. The Wasserstein distance between Pn and the distribution corresponding to the vacuum state by inspection is the cost of moving P of n to that vacuum state, and it's just n. So the total Wasserstein distance in that state is just n Pn equal to the average value of n. Similarly, W1 between the Fock states j and k, two Fock states, is just mod j minus k. That's a trivial statement. And here's a very useful result in calculating these quantities. Consider two normalized photon number distributions, P of n and Q of n, with CDFs as shown there, with the summation running up to n from 0 upwards. By definition, the Wasserstein distance between these two distributions is mod P minus Q integrated, summed over n from 0 to infinity. Then, given this, in those cases where P of n minus Q of n does not change sign for all n, in other words, one of them is like a convex hull of the other, for instance, then Wk1 can be simplified, the modulus can be removed, and you can just write it as the integral of the difference between P and Q, the summation of the sum over the difference between P and Q. And what does that tell us? Before we interchange the order of summation, we must be careful about convergence of this sum. And again we write the CDF in terms of 1 minus the survivor function and use the survivor function. And eventually with a little bit of manipulation you end up with this expression here. And a little more algebra tells you finally the simple result that the Wasserstein distance between two photon number distributions P and Q is just the magnitude of the difference between their average photon numbers in the two states, which means we can read off a large number of results right away for all sorts of states. But these conditions have to be satisfied by their distributions. And what's interesting is this result can be extended to the case of a continuous variable on a time and on some interval with a normalized PDFs f and g. If it turns out that x can only take on non-integer values and the curves of f of x and d of x don't intersect each other, unlike the case of the particle in the box which we saw earlier, except at the endpoints of the interval, then the Wasserstein distance between the two distributions is just the modulus of the difference between the mean values with respect to these distributions. Yeah. You can immediately apply it. Here's an illustration of this result, a made-up example. Consider the family of slowly varying or heavy-tailed distributions. F of x is m minus 1 over x to the power m, where m is a number greater than or equal to 2, greater than 2 strictly to start with. So x runs over 1 to infinity here, and it's a gentle power law tail. Here. Corresponding CDF is 1 minus x to the power 1 minus m, and the mean value is average value of x over this distribution is 1 plus 1 over m minus 2. Then for all n greater than m, the Wasserstein distance is the difference between these two mean values, which is 1 over m minus 2 minus 1 over m minus n minus 2. The divergence at m equal to 2 captures the fact that the PDF f2 of x has no first moment at all, no finite first moment. It goes like 1 over x squared, and that's not fast enough for the divergence, for the first moment to exist. It's normalizable, but it doesn't have a first moment. And that's very distinct from what happens for m greater than 2. So I call this a sort of transition point, and this indicator, this W1, detects that. If you do the same calculation for Kullback-Leibler and for Bhattacharya distance, it doesn't show up at all. M equal to 2 is not a special point at all. Whereas we know that it is moving from one universality class of distributions to another when you go to m equal to 2 at that singular point. So it's captured, this sort of thing is captured. Physically what happens is if you take the pile n and shovel this earth back towards m equal to 2, you'll have to shovel arbitrarily far, pour the mud arbitrarily long distances, causing the Wasserstein distance to diverge in this case. Similar phenomena occur when you look at the Wasserstein distance between two stable distributions of different indices, the Gaussian versus those below alpha equal to 2. We have similar phenomena happening. But this example I think is interesting because it's a very simple, obviously calculable example right away without fancy mathematics. Let's look at blackbody radiation. Again, we can write the answer down by inspection. You can take the frequency distribution of blackbody radiation at a given temperature, which we all learn in our BSc courses in statistical physics, I of nu, I sub t of nu. It's a unimodal distribution in the probability density function in the frequency nu. The only frequency scale is kt over h cross in this problem. So all answers like the mean, mode, median, etc. of this distribution must depend on kt over h cross, nothing more than that. And by our mean value, by the theorem we proved a little earlier for two non-overlapping densities, it turned out that the Wasserstein distance is proportional to mod T2 minus T1 minus T2. It's as simple as that. You can also ask what happens to the corresponding wavelength distribution, and that's slightly different in form. There is a 1 over lambda to the 5 and so on sitting there, e to the minus h, 1 over lambda t, etc. If you ask for the Wasserstein distance once again, it's just the magnitude of the mean values between these two characteristic temperatures, reciprocal, so it's T1 inverse minus T2 inverse. So these unimodal graphs can be disposed of without calculation actually. Returning to photon number statistics, we can write down other results. For a standard coherent state characterized by a complex number alpha, which is a displacement operator acting on the vacuum state, we end up with the Wasserstein distance between the vacuum state and this coherent state, the photon number distributions, to be proportional to mod alpha squared, which is the mean number of photons in the coherent state. This distance does not depend on the phase of alpha. So you have a situation where you have 2 points, every point on a circle with the same mod alpha is equidistant in that sense from the vacuum state. Consider the corresponding Kullback-Leibler divergence, and it turns out interestingly to be exactly the same answer as mod alpha squared. Just turns out that way. It doesn't happen all the time. For two coherent states, it's the magnitude of the moment of the magnitude of the difference between the mean values mod alpha squared and mod beta squared. For the squeezed vacuum state, where you take the vacuum and apply the squeezing operator S on it, which is e to the psi a dagger a squared minus I star a squared, the distance from the vacuum is given by, once again from this mean value statement I made, sine hyperbolic squared, the modulus of the parameter characterizing the squeezing, degree of squeezing. The Kullback-Leibler divergence between the vacuum and the SVS can be read off from the n equal to 0 component of the photon number distribution of the squeezed vacuum state. We now find a slightly different function instead of sin squared, you get log cosh mod psi. Yeah. There's a difference here, however, because it turns out that they have the same leading small xi behavior, but when the squeezing becomes very large, the Wasserstein distance is a much better discriminator because it blows up exponentially in the parameter, whereas the Kullback-Leibler goes like the linear function of the parameter here. All these states that we have considered so far are pure states. As an example of a mixed state, consider the thermal state at temperature T, in which the number of photons of a given frequency, nu and polarization state has the geometric probability distribution, the well-known Bose formula or geometric distribution here, where n bar is the Bose function. The density matrix corresponding to this case is rho thermal equal to, you put in the probability function P of n and then take the projector over the Fock states. And then the Wasserstein distance between the vacuum and this state is then the average number of photons in that frequency in the radiation, which is not a surprising result. For comparison, we find the DKL has a 1 added to it, nothing more than that here. Displacing the thermal state gives the displaced thermal state, known as the Glauber-Lach state, with the density matrix which is the displacement operator acting on either side of the thermal density matrix. And you work out what W1 is in this case with respect to the vacuum, and you get the average value of photons, average number of photons in black body radiation at that temperature, plus mod alpha squared coming from the coherent state part of it here. Similarly, we can play this game, calculate the WD between the vacuum state and many other states of interest, such as generalized coherent states, photon added coherent states, squeezed coherent states, displaced squeezed states, squeezed thermal states, and so on and so forth. There's a whole zoo of these things you can write down. Yeah.
Displace thermal state factor in nature anywhere.
We can create it.
Create.
Yeah. We can create it in the lab. Yeah. We can coherent states, every coherent state. Displaced thermal state, well, noisy, if it's noisy, if there's thermal noise in the problem, you get the Glauber-Lux state. Yeah. We can do fine things like we can add a photon to a state. I'll talk about photon added states in a minute. Yeah. We can ask, what does this whole thing look like in the position representation, or the X quadrature as they say in quantum optics? Obviously depends on the WD obviously depends on the basis and representation used for the random variable. So are the quantifiers of the distance between the two states of the system. For example, if you consider two Fock states, the vacuum state and then the zero photon state and the n photon state in single mode radiation, in the photon number representation, W1 is equal to n itself trivially. But in the representation given by the quadrature X, which is A plus A dagger over 2, the normalized PDF is just the harmonic oscillator PDF, as we all know. It looks like this for different values of n in terms of the Hermite polynomial, which are the eigenfunctions for the Gaussian multiplied by that are the eigenfunctions of the energy for a simple harmonic oscillator. And here's a graph for n equal to 50 and n equal to 0, the ground state. Notice the sharp peak in the ground state, the Gaussian function, and then the function, this function here with the Hermite polynomial squared multiplying it for n equal to 50. You can see that the probability mass has moved away, far away. We've already calculated from the oscillator problem that this whole answer should go like square root of n. But let's see what happens here. If we plot it, here's what it is for different n's. You can see that it's reaching the square root of n. Once again, I explained this on the basis of semi-classical physics. The ground state, the photon, most of the probability mass is concentrated around the origin in the ground state, and x is in the turning points are for high excited states are at plus or minus square root of n here. This immediately says that Wn must go like n to the half asymptotically.
Interesting to contrast it with radium.
Exactly, yeah. Where it goes like, yeah, where it goes like n squared, and this goes like n.
Just a related question. Is there a natural way to measure the Wasserstein distance experimentally? I mean,
Indirectly, yes.
so you can look at the quality of your.
The easiest, but in any, if it depends if the formula for the mean value works for the Wasserstein distance, then all you have to do is to measure the mean, and you can calculate it. But in more complicated cases, I know of numerical ways of getting it, but I'm not very sure of how we measure it directly.
You can use it as diagnostics only if you can measure in arbitrary systems.
I'll comment on this, please remind me, I'll comment on this at the end, what we can do with it in real problems as opposed to case studies we have been talking about here. If you compare it with what happens to the Kullback-Leibler divergence, that's an integral of this kind, and the graph looks exactly the same as in the case of the Wasserstein distance. However, and if you do this for instance, if you go on and do this for the Bhattacharya distance, you again get this integral, and you do that, it looks like the same thing before. But there's a huge difference. The asymptotic behavior of both KL and dB is a linear function of the log of n. In contrast to W1 goes like square root of n. This makes them much less sensitive quantifiers than W1 for the corresponding states. So the shape of the graph looks like a square root going square root, but it isn't, it's logarithmic. That's because of the log factors and the definitions of these quantifiers. So I put it to you that these two other quantifiers are not very satisfactory or very sensitive in detecting what state we are talking about. The whole idea is to build up a glossary of these Wasserstein distances asymptotically, and then match an experimental pattern with to find out what class of what the state actually is, to guess what the state is working backwards. That's really the purpose of the whole thing. So before I go to concluding remarks, I really should mention that the motive here was to take tomograms, which are actually scans, medical scans, and classify the patterns that you get in tomograms when you have different states of light, like for instance coherent states, squeeze states, photon added coherent states, and so on and so forth. Build up a dictionary of that, so that without the very difficult task or error-prone task of state reconstruction, quantum state reconstruction, which is the catching point, you can look at the scan itself, and just like a doctor says you have a fracture by looking at the scan, you can predict what the state is to some extent. In particular, we would like to know if the state is time evolving and undergoes sort of time evolution and goes through non-classical phenomenal states, like revivals, for instance, or fractional revivals and so on, sudden entanglement death, for instance. Can the Wasserstein distance be an indicator telling you what's happening backward without reconstructing the state here? In honesty, I should mention that we've tried this out in various cases, such as coherent state propagating through a Kerr medium and so on. And it turns out that while the Wasserstein distance does quite well in terms of revival phenomena and so on, it flunks out when you look at entanglement. For entanglement, not surprisingly, which has to do with the information theoretic considerations, the Kullback-Leibler has a much better divergence here. Of course, the gold standard is, as we know, this the subsystem for Neumann entropy, which is the gold standard of measuring entanglement, ascertaining if entanglement is there. But the Wasserstein distance doesn't fare so well at all in the cases we've looked at. But it fares spectacularly well in the case of revivals and so on, much better than those other things do. So with that, So the Wasserstein distance, the Kullback-Leibler divergence, and the Bhattacharya distance are quantifiers of the degree of closeness of different probability distributions of a given random variable observable of a system. Yeah. In general, they provide useful information for the comparison of the respective photon number distributions in appropriate pairs of quantum states of radiation here. But the Wasserstein distance supplements, augments, and in some cases outperforms more traditional distance quantifiers in the space of distributions. So means it merits more attention. That's the conclusion that I'd like to end with. More attention than has hitherto been paid to it, not only in tomogram interpretation and image reconstruction, but also as an exercise in quantum mechanics itself. We do everything with the probability density function, with the wave function, the eigenfunctions, etc., except compare what these distributions look like, which is a lacuna in the working. And I think this forms a useful bridge and fills a usefully fills a gap in our study of quantum mechanics. Now the real task is to build up this dictionary, the glossary of interpretation of momentum, for instance, pattern recognition, etc. So a lot of work is going on, especially on the quantum generalization, so that we don't refer to probability distributions at all, but directly talk in terms of the states and so on, multi-pattern systems. And that's the topic I have touched on here today. So with that, I'd like to end. Thank you.
It's a new current topic that we have learned from Professor Balakrishnan. So if there are any further questions on the talk, please.
Just a very basic question. So why not just subtract the PDF itself? Why the cumulative distribution function?
Because the Wasserstein distance is defined in terms of the quantile.
Or why not take a distance where you just do small f minus small g mod of that?
What is that going to give you?
Won't it tell you how different the distributions are?
It will give some difference, but it doesn't tell you what the...
It doesn't have some nice property?
It doesn't have a property of a distance.
Triangle inequality.
Right.
Yeah.
mentioned about thermal radiation comparing to two temperature. We know about cosmic background radiation, 2.7 degrees. Of course, it's changing with time very slowly. But if I take a burning coal, there is a black body radiation. So it's cooling down. So maybe one can do some experiments with burning coal to measure these distances. Because as it's cooling down, the temperature effectively changes
Yeah,
black body temperature. It's very difficult to do with cosmic background radiation because the time scales are too long.
But at every stage it's still in thermal equilibrium, quasi-equilibrium. So the black body radiation formula will be valid except that the peak will shift according to Wien's law.
Correct, yeah. Just to, for at the level of graduate student experiments in the masters and so on, it may be nice to see this. People focus on distribution, but this distance between two
Yeah,
distributions.
yeah.
would be nice.
How one merges into the other. Yeah, sure.
Thank you.
Do you have a pictorial or a graphical example of a place where the tomogram can be interpreted in terms of these distributions and how one does better than the other?
How one distribution goes to the other.
Yeah.
Yeah, we have numerically one can calculate what the Wasserstein distance is
No, I
at
mean,
every stage.
actual tomogram done this way and some other way, and how you can compare. This is the application, right?
Yes, yes. There is an experiment,
Is there
I
an
don't
example?
remember the reference now, we refer to it in our papers, where this has been done, yeah, in terms of the tomogram. So, but you see, we have to be sure that the tomogram itself, you have to be sure that the distinction is unique in some sense, subject to many interpretations or different. So if you're not told anything about the state of radiation, it's very difficult to say what it is. For instance, if I take a coherent state and I add a photon to it by photon addition, you get a different distribution altogether you get a different value for the mean value, for the mean number of photons, and you get a different distribution altogether. And now, you can also change the parameter of the coherent state and ask how close does that changed value, how close does that distribution approach to the photon added distribution? Is there an optimal value? And there is one like this. So if you're given a tomogram for these two cases, one with the photon added and one with a modified parameter of the coherent radiation, which is difficult to say immediately. Just by looking at the mean value is not going to be enough. So I don't know what other parameters have to be looked at. So some prior knowledge is needed of what we're talking about. I'm not sure if that answers your question, but people have started doing photon addition as well as photon subtraction. Intriguingly, we found that if you take a coherent state and add one photon to it or subtract one photon from it, the distributions don't change very much. In the case of one photon only, if you put in two photons, that's different, it changes immediately. And both these states have been seen in the lab, one photon subtracted as well as one photon added. And they have this distinct signature different from the coherent state.
So regarding your photon number distribution, so the Kullback-Leibler distance and this W1 distance versus sign distance, which one is more robust if I perform the photon number measurement?
Well, that's a good question. Well, if you make the photon, if you give the photon number distribution, you estimate the photon number distribution.
Yeah, I have photo counting measurement.
Yeah.
And let's say there is some noise there, some
Okay.
error there.
Okay. If there's noise, The Kullback-Leibler will be finer.
I see.
Yeah.
Okay.
It will be fine, it's a finer measure. It's not a proper distance, but that doesn't matter.
Yeah, yeah.
So it will be finer in that case.
Okay. Thank you.
But in many other cases, it's not. If you change, if you shift a distribution, you have a symmetric distribution centered about the origin, and you make a skewed distribution away from the origin, for instance, then you ask which is more sensitive, the Kullback-Leibler or the Wasserstein distance. The Wasserstein distance is more sensitive
I see.
in that case.
And if I have, let's say, some upper bound on the average photon number, that this, our state cannot have more than that,
Right.
then which one will be more useful, you know?
Well, if you have bounded distribution, formulas are straightforward to calculate, so why should it make any big difference?
No, I mean, which one means that if I want to distinguish two states, or two, I mean, here in this case two states. So if I have, let's say, a bound on the average photon number, so then will it be this Wasserstein distance which will give you better result, or this Kullback-Leibler?
You're cutting off the photon number distribution at some point.
Yes, yes, yes.
Well, better in what sense?
I mean, better in the sense that, you know, I want to distinguish two probability distributions, right?
Yeah, yeah.
So in that sense, so which will give me better distance in
Now,
that.
what are the two distributions you're talking about? One with any number of photons and the other with a truncated number
No,
of
I
photons?
have, let's say I want to distinguish between a coherent state and a squeeze state. Okay?
Okay.
But I have given that the average photon number
okay.
cannot go beyond that.
so- Okay. Can't say offhand because it will depend on the behavior of the cumulative function, which is getting cut off at some point, and then the nature of the integrand in the two cases, log ratio in one case, and then the other one is just the modulus.
Yeah, because practically we will have some bound on the photon number, right?
Yeah. Yeah. In all these calculations, there is a finite bound on the photon number.
Yes.
On the My gut feeling is that the Kullback-Leibler will be less sensitive than the Wasserstein distance in that case, because you have a finite number anyway to shift. You can compute it exactly. The Kullback-Leibler divergence tends to have very sort of characteristically logarithmic dependence on whatever parameter you're talking about. So it's a very weak dependence. Whereas the Wasserstein, as you can see, of course, admittedly these are artificial examples, but the Wasserstein has got power law behavior most of the time. The whole thing needs to be in practice generalized to multivariate case. Some results are known, but I'm told that the general problem is not solved yet in the multivariate case. And these WGANs and so on, they deal with this problem using machine learning and stuff like that. But
Okay, thank you.
univariate case pretty much settled. We know what it is. But the quantum analog of it is worth looking at. It's very intriguing and so on. For instance, if you add an array of spin chain and all the spins are up and then one of them goes down as opposed to all of them going down, which one is closer to the original? It's not immediately obvious. So it's a hard problem to be solved.
Hello, Professor.
Yeah.
I had mentioned at the last that for in entanglement, decay is better than Wasserstein distance. So like you've mentioned in the last example that W1 is sensitive than DKL, and in the slowly decaying distribution it captures the divergence as m equal to 2. That's why Wasserstein distance is better. So how in entanglement, can you help me understand with an example how it is better?
Yeah, we've looked
DKL
at-
is better in entanglement.
We looked at, this is purely numerical work, we looked at time evolving states. You start with the coherent state of radiation, put it through a non-linear medium, and you do the time evolution using the Kerr-Hamiltonian, for instance. Then it turns out, purely numerically, that features such as wave function revivals and fractional revivals and so on are signaled very strongly by changes, drastic changes in the Wasserstein distance. On the other hand, if you start with an entangled state or a state which is unentangled, a system which is unentangled, a bipartite system, it gets entangled as a function of time and then it comes back to its original value, etc. The Wasserstein distance doesn't do anything spectacular at all in such cases. But then the Kullback-Leibler does immediately. As would the subsystem for Neumann entropy and this subsystem linear entropy. They both may show up very strongly, but not the Wasserstein distance. So it's not a universal cure, it's just something which supplements and augments the other two quantifiers. In this game you need all the help you can get.
Thank you.
Okay, so,
Sure.
Bhattacharya is a physicist or a statistician?
Yeah.
Bhattacharya, is he a physicist or a statistician?
Statistician.
Okay, that's right.
He worked in the Indian Statistical Institute, I think. Yeah. And he found a remarkably cheap way of calculating, quantifying the difference between. Pardon me?
I said the results are independent. Physicist or mathematician.
I don't know the precise context in which he came up with it. I'm sorry, I should have read the history up a little bit more. But, but it's a very remarkable quantifier.
Ali Hassan, he reads about this optimal transfer theory,
Yeah.
where distributions. So he has separated protein coding problem.
Oh, okay. Okay. It's interesting that such a simple problem of moving one pile apart to another pile is not a solved problem. Immediately.
Fieldsman has been given for some work there in mathematics.
Yeah, the French mathematician.
What's the name? Yeah, some French.
He's always gaudily dressed. That's all I remember.
Cedric
I
Villani.
don't remember his name.
Cedric Villani.
Huh?
Cedric Villani.
Ah, that's him. That's him. Villa. That's him. Okay. Thank you very much.
Thank you.
So,
I have to be very careful in just climbing down staircases.